Bismillahirrahmanirrahim. Assalamu alaikum wa rahmatullahi wa barakatuh. We have had a discussion of already 2 weeks and we have gone through several concepts. And this week, end of this week, you'll have your assignment one due. So you guys have to go through this and make sure you are able to articulate the synchronization concepts and submit the assignment in time. Uh, we'll start this week's lesson here with just a review of what we have done plus some more. So a sequential version of an algorithm, if you want to parallelize it, change it to a multi-threaded version or a concurrent application, then we have to carry out some steps. So test if our concurrent algorithm generates correct results. If you want to create a concurrent version of a sequential algorithm, you have to first measure whether it can produce the same results or not. Also, before you even start, you have to decide whether concurrent algorithm is required even. Is this such a case or not? And when you want to measure the throughput of both algorithms to see if the use of concurrency gives us a real improvement in the response time or in the amount of data the algorithm can process in a time. So when you have a sequential algorithm and you want to convert it into a parallel algorithm, you have to go through this almost like a software development kind of approach where you analyze the requirements, you analyze what the sequential algorithm does, you create a design for your parallel algorithm, how you want to carry it out, and then you implement it. And design here means the planning and the coding, and implementation here is implementing it in a specific programming language, for example. And then you'll test it out and see if it produces the result the way you want it, and then you tune it. And the tuning is after you test it, you find out some issues, and then tune will happen because you'll carry out tuning after testing and checking whether it's performing the way you expect it. So what does analysis do? So in analysis, you look for the parts of this code that can be executed in a parallel way, and you pay special attention to those parts that are executed most of the time. By implementing a concurrent version of those parts, we are going to get a greater performance improvement. Therefore, that's why we want to convert it into a parallel application in the first place. In the design phase, you'll plan how you will do that parallelization. Some parts and some structures of the codes will be changed. And what you do normally is you'll do two things. One, you'll decomposition the tasks, or maybe you divide the tasks in several sections, or plus you may also decompose the data. And task decomposition means splitting the code into two or more independent tasks that can be executed at once. Some of these tasks have to be executed in a given order, or you have to synchronize mechanisms to get this behavior. Data decomposition, on the other hand, means when you have multiple instances of the same task that work with a subset of data set. This will be a shared resource, right? So you have to make sure that this data is implemented in a critical section. And this is what we have seen when we have examples of multi-threaded application that access shared variables, and the effect is not as desired. So if you want to have the desired impact or effect or expectation, you have to make sure you implement it in a proper way where the critical section is identified and synchronized. Objective of implementing a parallel version of an algorithm is to achieve improved performance. So you should use all the variable available processors or cores. So in single CPU, so there might be more cores. So this is how your algorithm has to be designed. If you split the algorithm into a lot of smaller tasks, the extra code introduced by the synchronization can provoke performance degradation. Again, this design impact you have to think about. After you have designed it properly, thinking all those aspects, you'll implement the parallel algorithm using a programming language, and if it is necessary, you may use a thread library for implementing it, of course. And again, testing, as we said, you'll test if it is producing the same result as the output you get from the previous sequential algorithm, and then you have to measure them. So what are the metrics to measure? We will come back to them. But tuning here refers to once you check on those things, maybe the metrics doesn't match up, or maybe the algorithm doesn't give the expected outcome. Now you will tune it, and based on these metrics, you will tune it. For example, speed. You know, this is a metric for relative performance improvement between the parallel and the sequential version of the algorithm. Amdahl's law. This is used to calculate maximum expected improvement obtained with the parallelization of an algorithm. And then you have this Gustavus-Box's law, which is addressing a limitation in Amdahl's law, and that limitation is it has this limitation where it supposes that you have the same input data set when you increase the number of cores. But normally when you have more cores, you want more data, the scalability should be there. So this can be used as a guideline when you are measuring these algorithms. And of course they have several formulas which you have to apply, which we are not studying in detail. So what do you expect from parallelization? You expect from parallelization to be have a more efficient algorithm. The parallel algorithm must end in less time than a sequential algorithm. The first goal of parallelization of an algorithm is that its running time is less than the sequential one, so it can process more data in the same time. Simple, it should be simple. So when you implement an algorithm, you must keep it as simple as possible. It doesn't mean it's really simple. It may have complex coding or complex implementation, but it should have a simpler way to organize the code and modular way of creating the coding, implementation. Portable, sometimes you may be able to take this application into different platforms if you implement it in Java, for example. So scalability, again, what happens when your algorithm, if you increase the number of cores or if you increase the number of data, amount of data, this is also something you have to think about. So all these individual items, you should know what they are, how they are measured. Okay, and we have seen this example. So this was where we said if you have a scenario where you have a class without synchronization and with synchronization, then you get the expected outcome when you add the synchronized word here. So on this class on the right you have the synchronized keyword added, because when you actually uh, claim money here or fund additional money, in both cases you are actually changing the details of this account. Therefore you have to make sure that you synchronize the variable budget, so that when one is the tasks are using that variable, the others have to wait. Okay, so this is an essential part. This coding part is essential. Your assignment is based on that, so make sure you practice this quite well and see if you can implement it yourself. Okay, Java concurrency API. This is something new for you as a additional part. So in terms of new stuff that Java has introduced, we may be able to uh, relate to them from the previous slides. So Java programming language has very rich concurrency API. It contains classes to manage the basic elements of concurrency, such as thread, lock, semaphore, and classes that implement a very high level of synchronization mechanism, such as the executor framework or the new parallel stream API. So you just know these terminologies. We don't really have to use them, okay, in the detail sections. We just know that they exist. The basic classes in the Java concurrency API are: you have thread class, you have runnable interface, thread local class, thread factory interface. So you have to know a little bit of what they are and each one of them do in a rough idea. Okay, so when you are synchronizing, and there can be many ways to do the synchronization. So Java concurrency API includes different synchronization mechanisms that allows you to define a critical section to access a shared resource or synchronize different tasks in a common point. So most of the synchronization mechanisms that you can think of when you think about synchronization mechanisms available in the programming language Java, for example, you have this synchronized keyword available. We have semaphore class, phaser class, countdown latch class, lock interface. You have cyclic barrier class. Example. So these terminologies and names you must remember. Synchronized mechanisms, some of them, if you try to detail out, you can say, for example, the synchronized keyword is most commonly used in simple implementation. So a synchronized keyword allows you to define a critical section in a block of code or in an entire method. You can just give it as a block or as a part of a method. The lock interface provides a more flexible synchronization. So in addition to having simple synchronization blocks, you could implement a more complex ways of synchronization where you implement using locks. So there are three options here. In this case, one is Reentrant lock to implement a lock that can be associated with a condition. Reentrant read write lock separates read and write operations. Stamped lock, which includes three modes for controlling read and write access. In addition to other synchronizer mechanisms, you also have the semaphore class, which implements the classical semaphore to implement synchronization. Countdown ledge class, which allows a task to wait for finalization of multiple operations. Cyclic barrier class, which allows the synchronization of multiple threads in a common point. And then the phaser class, which is allowing you to control the execution of a task divided into phases. Right. So what is executors? This is also something we may have seen. So executors framework is a mechanism that allows you to separate thread creation and management for the implementation of concurrent tasks. So you have that executor and executor service available to you. So executor framework is a mechanism that allows you to separate the thread creation. You create threads separately and manage separate threads separately. And what you do is, in this case, use the following classes available. For example, executor and executor service are two example interfaces available for us to use. They include methods common to all executors. We will have a look at this in the next lectures when we see a little bit of implementation of executor and thread pools. We are not going to go into details, but with very rough snippets of code where you will see how the executor is kind of implemented. So you'll get an overall idea. Thread pool executor. This is a class that allows you to get an executor with a pool of threads and optionally define a maximum number of parallel tasks. Scheduled thread pool executor. This is a special kind of executor to allow you to execute tasks after a delay or periodically to do a thread execution. And executors in this case is a class. Remember, there is executor and executors. So executors is a class that facilitates the creation of executors. Okay, so basically it provides static methods. Callable interface. This is an alternative to the runnable interface, a separate task that can return a value. The difference is runnable interface doesn't return a value, but callable interface returns a value if needed. Future interface. This is an interface that includes the methods to obtain the value returned by a callable interface and to control its status. The fork or join method or join framework. So a special kind of executor is specialized in the resolution of problems with a divide and conquer technique. Includes a mechanism to optimize the execution of the concurrent tasks that solve these kind of problems, specially tailored for fine-grained parallelism, as it has a very low overhead in order to place the new tasks into queue and take queued tasks for execution. So you can see then some advantages and advanced features available here in this framework. And main classes involved in fork join framework is we have this class called fork join pool, which implements the executor that is going to run the tasks. Then you have fork join task class that can be executed in a fork join pool. Fork join worker thread, a thread that is going to execute tasks in a fork join pool class. So again, it's an additional way of implementing synchronization. Parallel streams. So parallel streams is also another example. So it realizes operations in a parallel way. The most important elements involved in the use of parallel streams are stream interface, which is defines all the operations that you can perform on a stream, and there is a optional interface, a container object that may or may not contain a nominal value, collectors, a class that implements reduction operations that can be used as a part of stream sequence of operations. Then you have this lambda expressions, and it's not already highlighted because it's not a class. Lambda expression is a way you present expressions. So streams has been thought to work with lambda expressions. Most stream methods accept a lambda expression as a parameter. This allows you to implement a more compact version of the operation. So it's just a way of passing variables. Concurrent data structures. Normal data structures of the Java API, like array list, hash table, and so on, for example, which are data structures in Java, are not ready to work in a concurrent application, but you need concurrent data structures in a concurrent application. So if you use it, you'll be adding a lot of extra computing time to your application. If you don't use it, it's probable that you'll have a race condition in your application. So Java Concurrency API includes these kind of data structures that can be used in concurrent application without any risks, meaning they are thread safe. So they are divided into two groups. One is called blocking data structures, which is methods that block the call in task when, for example, the data structure is empty and you want to get a value. Or non-blocking data structure, if the operation can be made immediately, it won't block the code in tasks. Otherwise, it returns the value, a null value, or throws an exception. Concurrent data structures, or concurrent linked data queue, DQ, concurrent linked queue, linked blocking queue, linked blocking queue, linked blocking DQ, priority blocking queue. So these are all examples of different data structures which can be useful for implementing concurrent data structures. And again, we are not really going into the detailed implementation of those things. You just study them as concepts here in this module. Okay, the last section of this chapter is called the Java memory model. So a memory model is what describes how individual tasks interact with each other through the memory. So concurrent applications in a computer with several core processors can have a problem with memory caches, can cause data inconsistency if the memory is not shared properly. When a task modifies a value in the variable, it's modified in the cache, but it's not modified in the main memory immediately. If another task reads the value of that variable before it's updated in the main memory, it will read the old value of the variable. A memory model describes how individual tasks interact with each other through the memory, and when change is made, one task will be visible to the other tasks. And the way you force this behavior is in the Java memory model. You have these things called volatile keyword, synchronized keyword, and final keywords available that could indicate that these are shared variables, therefore they have to be updated from the cache. Ensures that a properly synchronized concurrent program runs correctly on all architectures. So if you have Java memory model, it provides these keywords for us, and also it ensures that a properly synchronized concurrent program runs correctly on all architectures. It creates a partial ordering of the volatile read, volatile write, lock, and unlock instructions as nominated as happens before. So that's what the memory model is about. So basically that's the idea of this lecture, and then that is chapter 1 and chapter 2 coverage, and we will have a separate look into the chapter 3 in the second class. And so for now what you will do is you go through this chapter 2, which has been taken from this book, and you don't have to buy the textbook because the coverage here is enough for your studies and requirement. You may read if you have the book, and then you can go through this data in order for prepare for your assignment too. And then on the Moodle you can find quizzes related to the chapter 1 and chapter 2, which we would like to review before we go into the chapter 3. So our target for this session will be to do the quiz and to go through the rest of the studies steps we have covered here at the end of chapter 2. Okay, so thank you very much. See you later.